manipulator. Okay, and it looks like this. Okay, so that is basically my way of showing a revolute joint. Okay, so that means it's rotating by an angle theta, sorry, theta 1 along the axis I've shown. And then I'm going to show, so then there is a prismatic joint. So one of the places where you did a prismatic joint was the pumping the swing, right? One of the pump was sitting and standing. That was a prismatic joint. You change the distance. So that is going to be shown this way as a box. And the axis for that is up and down. Okay, so it's oriented so that it goes up and down. And then I'm going to draw another box. Okay, this one is going to have motion in this direction, so D3. And then there'll be the end effector, which is here. Okay, so this looks very strange, right? How is this a manipulator? Well, as I said, if I drew the links showing each of these, okay, that's better. So if I draw the links which connects these joints, then it's going to look crowded, and that's why we just show the joints. So each of these, so I'll just write here, only joints are shown. Okay, links connect the joints. So if you notice the DH convention, we don't really care about the links, we only care about the joints. And that's why it's much easier to just draw the joints versus the links. So for a problem like this, where you're given the end effector, and I forgot to draw the distance, this distance is actually L1. Okay. The question is find the position and orientation of the end effector. Okay, which is shown there. So the problem is the same, except that the figure, it's a three-dimensional manipulator. Okay, so there we have. Now what I'm going to do is I'm going to start with the algorithm I wrote down, three steps. Step number 1 is assign axis. And so let's go back to the handout, which I just shared some time back. Okay, the first step is to assign a coordinate frame, right? So first assign ZI along axis of actuation. So there are three joints. And so we need to assign 3 axes. So the first one is going to be along theta 1, so Z0. The second one is going to be along D2, so it's Z1. And then third one is going to be along D3, so it's Z2. And we are done because there are 3 joints. Okay, next step is so that's completes 1A, which is done. Next is 1B. So 1B says assign base frame OOXOYOZ0. Okay, how do we do that? Well, Z0 is already assigned, like you see there. Assign X0 arbitrarily. Now we have the choice to assign the X0 arbitrarily. So one choice is, for example, here. Another choice is here, 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 here. I mean, you can do anything you want in a plane, of course, which is right angles to Z0. Okay, so feel feel free to use whatever you want. I'm going to stick to my notes, and I chose x0 to be along this direction, and which again, as I said, is an arbitrary choice. Okay. Okay, now if you want to assign y0, that's going to be at right angles to both of them, such that x cross y, we call your fingers, four fingers of your right hand from x0 to y0, your thumb gives the direction of z0. So we're done with B. Okay. Next step is to go to C. C says now assign coordinate frames OI, XI, YI, ZI. So that will be I equals 1, 2, that's it. So for that, we need to find the relation between Z's, right? So first of all, let's see the relation between Z0 and Z1. So Z0 and Z1, are they if they're not coplanar, there's Roman 1. If they're parallel, there's Roman 2. And then if they intersect, there's the Roman 3. So if you look carefully at the Z0 and Z1, we see that Z0 and Z1 actually intersect, right? They are intersecting. If you extend 0, it will intersect to Z1, which means that it actually fits in with 3 in the handout. And in this case, xi is chosen to be normal to the plane formed by zi minus 1 and zi. So we need to choose xi, in this case I equals 1, x1, to be right angles to z0 and z1. So again, there are multiple options. You can draw x1 this way, this way, this way, this way, whichever way you want. So the choice is arbitrary in terms of uh, which which direction you want in the plane, but it has to be right angles. So let me stick to, let me just choose it to be along this. Okay, that's just an arbitrary choice. Other choices are fine too. Okay, so we are done with 3. Now let's move on to Z1 and Z2 and try to identify how are Z1 and Z2 related. Again, we need to look at C1, 2, and 3. Are they not coplanar? That's not true. Are they parallel? They are not parallel. Do they intersect? Yes, they do intersect. Z1, if you extend, it intersects Z2. So it's again case 3, the Roman 3. And we can now draw the x2 at right angles to the plane formed by Z1 and Z2. So Z1 is this way, Z2 is to the right. And now the question is, what is normal to Z1 and Z2? It's either going to be this direction or this direction, right? Both those lines are right angles to Z1, Z2. So we have only 2 choices. Unlike the previous case, we had infinitely many choices. So you can choose either of them and it won't hurt the final answer. So I just decided to go with x2 in this direction. Okay, so I chose x2 like this, but x2 like this is also valid. Okay, we're done with that. We've exhausted all the actuated links, and now we go on to step number D in the handout. So this one basically is about assigning a coordinate frame to the end effector. Okay, so the end effector, we say we attach Zn, which is the end effector frame, to be the same direction as n minus 1. So in this case, Z3 will be in the same direction as Z2. And then we assign x3 based on the relation between Z3 and Z2. Okay, so we again need to go through see the options 1, 2, and 3. So we can see that here, we can see that Z2 and Z3 intersect each other. So the option which is valid here is number 3. And so we need to draw x3 at right angles to the plane formed by Z2 and Z3. So again, we have to either choose here, any of these options which are in this plane are valid. Okay, so I just put Z3 to be, or x3 to be along this axis, okay, which is again, as I said, is arbitrary once as long as it's in the plane. And then if you want, you can go back and assign y-axis. So x1 is here, z1 is up, then y has to be this way, y1, and then x is to the right, y has to be downwards for it to be consistent with the right hand rule, and then same for here. Okay, this, as you see, has no bearing with our dh table. If you want, you can draw it, but it's not required. So that's it. That basically assigns the coordinate train problem. So last class we did this three-dimensional manipulator problem. Here is the manipulator, and it looks strange because I have not shown the links, I've only shown the joints. Okay, so there are three joints. There's one revolute joint, which is here, first one, and we denote the revolute joint with a cylinder. The prismatic joint is shown by a cuboid, and so that's shown with the symbol D, indicating displacement or distance along X, Y, or Z. And then we have another link, which is another joint with a cuboid. So it's again a prismatic joint. So this is the way they call this is 1R 2P manipulator. The R represents revolute, P represent prismatic. So that's the terminology normally used for manipulators. Okay, so this is the caricature of the joints. I've shown you the degrees of freedom. So the motors can control theta1, d2, and d3. The only length which is given is L1, and the end effector is somewhere here. You got to find the position and orientation of the end effector for a generic theta1, d2, and d3. So those are things you control, right? And you want to find where the end effector is in order to do things like inverse kinematics. So I redrew the figure. I went through the handout, step one, which is about assigning coordinate frames. First, we assigned Z0, Z1, and Z2. Then, based on the relation between Z0 and Z1, that is, the Z's are the axis of actuation, so theta 1, D2, we basically assigned axis X0, X1, and X2. Okay. And once we did that, we went to the end effector and then established the axis Z3 and X3. So once we do this, we are all set to figure out the DH parameters, the alpha, A, D, and theta, which I'll do next. So I just copy pasted the same figure here. So it's easier for me to go proceed and find the parameters. So let me write this down here. We have AI, or in this case, since we are looking at link 1, let's just write it as A1, alpha 1, T1, theta 1. So let's put this down here. Okay, so I am right now reading off the handout. This is page 3 of the handout, where I have the cheat sheet to help me populate the table. Okay, and as I said, I like to use this particular sort of a mnemonic to remember how to set these values. So in this case, I equals 1. So x1, z1, z2. This is alpha 1. Okay, so from this figure, I'm going to now generate a1 and alpha 1. Okay, so what's a1? A1 is the distance between, I have to correct this. This is not right. This is Z1 and Z2. Okay. A1 is the distance between Z1 and Z2 along axis X1. Okay. So let's see what that is in the figure. The distance between Z1, hold on, I'm just one second. I think I'm doing something wrong. I equals 1. Yeah, that's what. So this is not right, right? When I equals 1, this should be Z1 and this should be Z0. I accidentally wrote it as Z2 and Z1. Okay, so I think I'm all set now. So A1 is the distance between Z1 and Z0 along X1. So Z1 is here, Z0 is here, and I'm going to find the distance along X1. So all I see is that Z1 is like this, Z0 is sort of parallel to Z1, and the axis X1 is this way. So if you view this thing from the right, you can see that since Z0 and Z1 are parallel to each other, the distance along X1, along this direction, is going to be 0. So that's 0. Okay, the next step is angle alpha, which is the angle between Z0 and Z1 along X1. Okay, so the angle between Z0 and Z1 along X1. Okay, so if you curl your fingers, something, just hold on, let me just check something quickly. Thought I got this right. Okay, yeah, it all looks right. So it's the angle between Z0 and Z1. So Z0 is here, Z1 is there, and that angle is going to be the angle by which I rotate theta1, right? So it's theta1. Okay, the next step is to, my bad. Okay, this is not right. I'm sorry about this. So this is the angle between Z0 and Z1 along X1. So you basically need to see how Z0 and Z1 line up. So they're actually 0, right? So if you curl your fingers along X1, right, then you can see that Z0 and Z1 is actually parallel. So the alpha 1 should be equal to 0 and not theta 1, as I said. Theta 1 will actually come in the second part. So this is completes the first two elements in the table. I'm sorry about that. I got slightly confused with the notation here. Okay, so we got that. Let's move on to the next part, which is so then I put I equals 1, so x1, x0, theta, and we have angle z I equals 1, so z0. So this is again using page 3 in the handout. I need to find for d1, I need to find the angle, the distance between x0 and x1 along z0. So x0 and x1. X0 is here, x1 is here, and we want to measure the distance along z0, right? Z0. So x0, x1, and this is z0. So the distance along z0 between these two axes, x0 and x1, is going to be L1, like it's shown here. So that is L1. And finally, we need to find the angle between x0 and x1 along z0. So right now, x0 and x1 are parallel to each other, but when the motor applies a torque, theta 1 will change. So x0 is basically going to be rotating, right? This way. So that's theta. So at this point instant of time, the way I've shown the axis, the angle is 0. So theta 1 is 0. However, as the motor applies a torque, theta changes. And so I would put here theta 1 instead of putting 0, because that's the thing which is controlled. Okay, so this basically gives me the 4 numbers for the first line of the DH table. I need to do the same thing for the second and third link. So what I did was I actually copy pasted this figure two more times. Here is the same figure drawn again, and I'm going to try to get A2, alpha 2, D2, and theta 2. Okay, so again, I'm sorry, again, we'll look at the page 3 figure. So I put I equals 2, So I have z2 z1 x1, and then the angle is alpha 2, I equals 2, so here will be 2 1. Okay, this looks correct. Okay, so I'm just putting I equals 2 in that page 3 figure I drew. Okay, let's move on and identify a2 and alpha 2 from this figure. A2 is the distance from z1 to z2 along x2. So the distance between z1, which is here, and z2 along x2. Okay, so I'm going to redraw that. Z1 is up, Z2 is something like this, and X2 points out of the plane. Now, since Z1 and Z2 intersects at this point, the distance along Z2, along X2, okay, as viewed from here, is going to be 0. Okay. Next is the alpha 2 is the angle between Z1 and Z2 along X2. So now the angle between Z1, which I've shown here, and Z2 along X2. So the best way to do that is to actually line up Z1 and Z2 such that they have either their tails, so tails is when there's no arrow, intersecting at one point, or their heads intersecting one point. So you can use either of the two ways to get the direction. So in this case, I put their tails joining each other or intersecting each other at that point. Okay, so now I need to find the angle between Z1 and Z2 along X2. Okay, so for a second, and I'm not able to do this because you cannot see me physically doing this, but take your right hand and curl your fingers from Z1 to Z2. Okay, so if you curl your fingers from Z1 and Z2 while keeping your thumb pointing along X2. So if you're doing that right, then you will see that you are curling your fingers this way. Right? So curl your fingers, your right fingers on your right hand from Z1 to Z2 in the direction I've shown, and you will see that your thumb naturally points along the direction of X2. Okay, so that is how you need to estimate alpha 2. It's the angle from Z1 to Z2 with your thumb pointing along X2. So you can see that that angle is 270 degrees. Okay, that's one way of getting alpha 2. The other way of getting alpha 2 is, some people prefer it doing this way. They want to find the smallest possible angle between Z1 and Z2. If you want to find the smallest angle, then you want to curl your fingers from here to there. This is again your right hand fingers from Z1 to Z2, but you need to now curl them in the clockwise direction, right? In other words, your thumb will point along minus X2 direction. So if that is the case, then you will write this angle as minus 90 degrees. Okay, so either of those two answers are valid answers. You can put either of those two, and that will not affect the final answer. Okay, so there are two ways of writing that angle. Okay, so this is one case where you will see that it's not 0, it's far from 0. And I think those are the cases which people have a hard time doing. So be very careful or understand this very well before you apply this. Okay, so that's alpha 2. Let's move on to D2 and theta 2. So I'm going to redraw the figure I drew on page 3. Again, I put R equals 2. So I have Z1 X X2 and X1. And then the angle is theta 2. Okay, so let's see what is D2. D2 is the distance from X1 to X2 measured along Z1. Okay, so let's see where X1 is. X1 is right here. X2 is right here. So let me draw that here. X1 x2, and the distance is measured along z1. So z1, I'm drawing z1, which is right there. Okay, so you can see that the distance along z1 is going to be d2. So put that there. And then finally, I need to find the distance, sorry, the angle between x1 and x2 along z1. You can see that x1 and x2 are actually parallel to each other. So since they are parallel, this angle has to be 0. Okay, so we're done with the second line of the DH table. Any questions here? This is probably the hardest one. Okay, but we'll do another problem where hopefully you'll get a hang of this. Okay, so let's move on, do the final link. So I want to find A3, alpha 3, D3, and theta 3. Okay, so let's go to page 3. I'm going to write sub in I equals 3. So we have x3, z3, just make it the way I have it in the figure, and then z2, alpha 3. Okay, looks right to me. Okay, so let's now find the distance A3, which is the distance from Z2 to Z3 measured along X3. So Z2 is right here, Z3 is right there. Let me redraw them here. Z2, Z3, and I need to find the distance along X3. Okay, and X3 you can see points in this fashion, points this way. So if you actually see this figure from this side, view it, then you can see that Z2 and Z3 align with each other. So the distance along this axis between those two axes, Z2 and Z3, is going to be 0. So that's my first value. Next, I need to find the angle between Z2 and Z3 along X3. So Z2 and Z3 are parallel, and clearly the angle between them is going to be 0. So that's 0. So that was easy. Okay, next let's find D3 and theta 3. So I'm going to redraw that same figure on page 3. Put I equals 3. So we have x3, z3, z2, alpha 2. Okay, so now we all set to find d3, which is, it should be theta 3. So d3 is the distance from z2 to z3 along x3. My bad, I am doing it incorrectly. So this is not supposed to be x, but it should be z. So z2 x 3 x2. Okay, looks correct to me. Okay, the distance between x2 and x3 along z2. So let's see, x3 is right here, x2 is right there, and z3 is z2 is here. So let me redraw that. X2 points this way, x3 points out of the plane, and then z2 points this way. Okay, so distance from x2 to x3 along z2, that's d3. And we can see from the figure that that distance is simply d3. So we'll write d3 for d3. And then theta 3 is the angle between x2 and x3 measured along z2. So angle between x2 and x3 measured along z2. But you can see that x2 and x3 are actually parallel to each other, right? I just draw the dotted line to show they're actually parallel as viewed from this way. So that means that the angle is 0. Okay, so that basically completes the third line of the DH table. So I'm going to put all that together now. So the DH table is now ready. So we have from the first page we did today 0, 0, DL1. Sorry, let me just swap this because that's how I wrote this down. L1 theta 1. Then we have 0. You could write 270 or you could write minus 90. It's up to you. D2 0, then 0, 0, D3 0. Okay, this part is clearly very trivial. And then the final step, once we get the DH table, is to use the H formula, which is H I with respect to I minus 1 equals, okay, so there is a formula which I will not write here because you can see the notes, see the DH handout. Okay, so I'll have to write 3 of these values, one for H01, H12, H23, because each of these will come from one of the lines of this TH table. So this is I equals 1, I equals 2, I equals 3. Once I get that, I can find H3 with respect to 0, which is H10, H21, H32, which is the multiplication of these H's, which in turn come from here. And if I do that, I get a 4 by 4 matrix, which looks like this. C1, S1, 0, 0, 0, 0, minus 1, 0, minus S1, C1, 0, 0, and then minus S1, D3, C1, D3, L1 plus D2. Okay, and so the position of the end effector is simply the last column of this 4 by 4 matrix. So it's minus S1 D3, C1 D3, L1 plus D2. And then orientation of end effector is going to be the 3 by 3 matrix, the first 3 rows, first 3 columns of this 4 by 4 matrix. Okay, where C1 is cosine of theta 1, S1 is sine of theta 1. And one more thing, which is when I say the orientation, I gave you a 3 by 3 matrix, right? But we can write the orientation of any object, as we've discussed before, using Euler angles. So we really need 3 numbers to describe the orientation, not 9 numbers like it's in this table. So when I'll be talking about inverse kinematics, I will show you how to convert this to 3 to 1 Euler angles. It's not very hard. It's pretty easy to do it, but I'll show it to you when we talk about inverse kinematics. But for now, this is just what I would have here. Any questions? Example 3. So again, I'm going to show only joints and not the actual links because that will clutter the whole figure. But this is good enough for us to do the DH. Here is a 3RR or 3 revolute joint manipulator. Okay, where the length, this length is given, and then this length is given, and then the end effector is somewhere here, so that length is also given. Okay, so the question is find the position and orientation of the end effector like usual. Okay, so how do we do this? Well, let me redraw this figure first. I should have also put the angles. Maybe I can do it later. I had to put the degrees of freedom, but I think it's obvious from the figure which sides corresponds to rotation. It's the circular part, which is the axis passing along the length of the cylinder, which is the axis of rotation. So let me redraw the figure L1. Okay, L2 and L3. Okay, and so let's start analyzing this or fitting the axis for this. So I'm going to go through the handout again. Start with step number 1, assign coordinate frames. So first, assign zi along axis of actuation of each link. So 1a is what I'm doing. So the first axis are going to be z0. Second one will be z1. Third one will be z2, and that's it. Next, assign base frame OOXO YOZ0. So that is pretty much arbitrary. You can assign X0, Y0 the way you want, but you have to assign Y0 first and then, assign X0 first and then Y0 is based on the right hand rule. So I have the choice of assigning Y0 this way, sorry, X0 in any of these directions, such that it is at right angles to X0. So I am going to okay, I'm going to assign it in this fashion. Okay, so that again is an arbitrary choice. So we've done that. We've done with step B. Let's go to step C. So step C says is how to attach frames X1, X2, and X1 and X2 in this case, because X3 is going to be the end effector. So we need to find the relation between Zi and Zi minus 1 in order to do so. So step number C is what I'm doing next. So first of all, let's try to understand how are Z0 and Z1 related. So Z0 and Z1 are at right angles to each other, or they are perpendicular. So then we can see that it corresponds to case number 3, where it says that Zi minus 1 and Zi intersect. So for Z0 and Z1, it's going to be case 1. This is what I put here. So if you read through 1C3, then you'll see that if Zi minus 1 and Zi are intersecting, then Xi is chosen to be at right angles to either of them, right? So since Z0 is approximately this way, you can choose X1 to be either pointing this way to the right, or you can choose it to be pointing to the left. Both are valid choices because they don't violate the rules. So of those two choices, I decided to go with X1 pointing to the right. Again, that's arbitrary. You could have as well chosen it to be the left side and it will not change the final answer. The DH table will change. However, the final value for the position orientation will not be dependent on how you chose the axis. Okay, so I chose X1 there. Next, let's try to find X2. So again, I go through the handout. I look at 1C and try to see what is the relation between Z1 and Z2. So you can see that Z1 and Z2 are essentially parallel to each other. So when they are parallel, there are infinitely many perpendiculars. We need to choose the perpendicular such that it passes through the center of Z1. So in this case, X2 is choice is pretty much that. Now you could have also chosen X2 to be pointing to the left. Okay, it's a perfectly valid option. It will actually work too. Okay, so I just chose it to be to the right as I've shown here. So for the next axis, I use 2. which is the relation between Z1 and Z2. So hopefully this will make it clear to you about how I went about choosing the axis when you are referring to the notes later on. Okay, so that's number 2. I've done with that, and it looks like I've done with all the axes I needed to. Let's now move on to step number D in the handout. Okay, step number D tells me how to attach the end effector frame. So end effector is right here. So the way you attach Zn, in this case Z3, is that you try to see the relation between Z3 and, well, you should attach the same direction as Z2. So Z3 will be essentially in the same direction as Z2. And then when you want to assign X3, you try to see the relation between Z2 and Z3. So you can see that Z2 and Z3 are actually parallel. So when you do D, you have to go back to C and then see that they are parallel to each other, which is going for step number 2, which is the Roman 2. And that means we need to assign X3 to be in this direction, right? So that it intersects X2 at the origin. Again, you could have taken X3 to be pointing towards the left, but this is a valid option to take it to the right. So left or right is the same thing. I'm just going to draw it here so that it sort of visually looks better. Sort of they are sort of in the same line, which is what they are. Okay, so that concludes assigning coordinate frames. Now let's go on to filling up the DH table. So I'm going to do it much faster than I did normally. I'm just going to do it in one shot, directly populate the DH table. And that's how I would recommend you doing it. If you want to break it down to steps like I did it in the last question, feel free to do it, whatever works for you. So I'm going to do it in one step. And that's how I recommend it normally, but feel free to take pages to figure this out. Copy. Okay, so let's draw the DH table. Link 1, 2, 3, AI, alpha I, DI, theta I. Okay, and I'm going to draw that same sort of trick which I used to figure out these angles. So here, XI, ZI, ZI minus 1, alpha I, and then the other one is ZI minus 1, XI, XI minus 1, and then theta I. Okay, so let's do it line by line. Okay, so let's start with first line. So first we have AI, which is the distance from Z. Now we'll have to put I equals 1. This is I, right? I equal to 1, I equals to 2, and I equals 3. So if you put I equals 1 here, we have Z1 and Z0. So we have to find the distance from Z0 and Z1 along X1. So Z0 and Z1 along X1. So you can see that Z0 intersects Z1. So the distance along X1 is going to be 0. Okay, next, we want to find the angle between Z0 and Z1 along X1. So Z0 is going up, Z1 is to the right. So you can see that at right angles. Maybe I should draw this here because this one is the case where you get a 90 degrees. So Z0 is up, Z1 is pointing outwards to the plane of paper, and X1 is to the right. Okay, so if you want to find the angle between Z0 and Z1, you can curl your fingers from Z0 to Z1 because that's the direction. It's from Z0 to Z1. So you have to go this way. And when you do that with your right the fingers on your right hand, your thumb invariably points in this direction. So then that angle is going to be 90 degrees. Okay. So this is how we got it. Okay, the rest of the ones should be trivial. Okay, next we need to find d1, which is going to be the angle between, or the distance between x0 and x1 along z0. So x0 and x1, and the distance is along z0. Okay, so you can see that distance between x1 and x0 along this axis is going to be L1. So I put that down there. And then finally, the angle between x0 and x1 along z0. Okay, so since this is a revolute joint, that angle is going to be theta 1. Right now it is 0, but when the axis rotates, it's going to be theta 1. Okay, the next one is, so that fills the first line. Next, go to the second line. Now I put I equals 2. So I need to find the angle between z1 and z2 along x2. So z1, z2, z1 is here, z2 along x2. Okay, so z1 and z2 are, well, first of all, the distance. So the distance between those two is going to be, between these two lines, is L2, because L2 is along x2. So then I'll put here L2. Then I need to find the angle between z1 and z2 along x2. So since z1 and z2 are parallel, the angle is 0. Okay, next I put I equals 2 in here. So I have the distance, so the distance or angle from x1 to x2 along z1. So x1 to x2 along z1. So x1 to x2 along z1. So the distance between this axis and this axis along z1 is going to be 0, because when you look at it from the left, as I've shown it there, that is going to be parallel, so 0. And then I need to find the angle between z1 and z2 along x1. Sorry, x1 and x2 along z1. So angle between x1 and x2 along z1. So that is basically is 0 right now because they are parallel. But when the z1 rotates, it rotates this way, right? Theta 2. That angle is not going to be 0. It's going to be theta 2. Okay, and so you can apply the same logic for z2 and z3, because since z2 and z2 are parallel, z2 and z3 are parallel, essentially the same line, same logic which applies for z1, z2 will apply for z2, z3. And so you can write this as L3, 0, 0, and theta 3. Okay, so I did not do that, but you can do it yourself and check if that works out right. Okay, so that step completes step 2. The final step, number 3, is to apply the H formula. So H I to I minus 1. So there's a 4 by 4 matrix which you want to copy down. If you, I would do this in MATLAB. Then I would establish what H10 is, H21 is, H32 is by using this formula for H, and also using the table. So you put I equals 1, 2, and 3 to get these values. Then find what H30 is, simply H10, H21, H32. And if you, in this case, I did not do the math here, I just kept it this way. So it'll come out to be something like this, which you can find using MATLAB. And then the position is simply D30, orientation is simply R30. Let me write this down. So do this computation symbolically in MATLAB. Okay, that's how it's to be done. It's much easier to do it that way. So anyways, this is the answer I was after. It comes from taking the multiplication, which in turn comes from the DH table, right? And so this is how you can do sort of the DH table faster than you do by doing it one at a time, but it's up to you how you want to do this. Okay, so I'm out of time.